Hello, this is AP Chemistry Notes, pages 23 and 24. We start off with a bit of a review of intermolecular forces. So to remind you, these are between molecules. Intramolecular is within, so the bonds are intra, the atoms are intra, the electron shells are intra, things like that. Between one molecule and the next is inter. So we have a molecule here and a molecule here. Anything going on between them, that is intermolecular. So just think international. That might help you relate to it. Now, the result that usually comes up here between two molecules is an opposite charge attracting. Fancy word for that is electrostatic attraction. And of course, the strength is based on Coulomb's law that's been discussed earlier. So we'll look at the three common ones: London dispersion, dipole-dipole, and hydrogen bonding. London dispersion is named after Fritz London, a person, not the city. And what happens is, just by chance, the electrons in a molecule may end up more on one side of the molecule than on the other. So for simplicity here, I have a very basic drawing of what would be a hydrogen molecule and another hydrogen molecule. And we're looking at what's going on with the electrons. So I just summarized it as two protons in the circle here, and another one here. Now, the two electrons in this molecule are buzzing around in their orbitals, but just by chance, if I were to take a picture, not that I can, but if I could, it might happen that the electrons happen to be a little bit more on the right side than they are on the left side. That would cause a very slight charge on the right side of negative, and I'm not even labeling it over here. Likewise, let's say in my other molecule, the same thing happened. I happen to have the electrons a little bit more on the right. Well, that would cause a slight charge of negative on the right and a slight charge of positive on the left. And what will win in this case, because of proximity, is the negative from the molecule on the left will be attracted to the positive from the molecule on the right. And so what's happening is just at this moment, that's why this is called a momentary dipole. Just at this moment, there's an attraction here. And in this case, it would be extremely weak in the case of two hydrogen molecules. The interesting thing about this is that all molecules do this because all molecules have electrons. And as molecules get bigger, these forces, which are sometimes called dispersion forces, they increase because you end up with more electrons, which causes what's known as a higher polarizability. So what that means is as you get a bigger molecule, you get more electrons, which means the more electrons can do what has been drawn here more drastically, causing the molecule to be even more strongly attracted to other molecules that have this temporary dipole, or any charge for that matter. So it's important to note that what I usually abbreviate, the LDF forces increase as molecules have more electrons. And the fancy way of describing that is to mention this polarizability here. And you could even work in Coulomb's law as needed. Next, dipole-dipole sounds kind of silly because it says the same thing twice. Basically, it just means a polar molecule and another polar molecule. So take HCl. An HCl molecule, negative towards the chlorine side, positive towards the hydrogen. So I've drawn two here in the box. There's a negative here, and that's always there. That's not temporary. There's a positive here that's always there, so you get this attraction. And with all else being equal, this is a stronger attraction than the London dispersion, but it's possible if London dispersion forces get strong enough because a molecule gets massive, that can become more significant. So it depends on the size of the molecule and how many electrons it has. Next one is called hydrogen bonding, and I've always found this one to be a little confusing because of the word bonding. So be careful here. Hydrogen bonding, think of it as an intermolecular force and not a new type of bonding. So don't think we have ionic bonding and covalent bonding and metallic bonding and hydrogen bonding. It's best to think of it as an intermolecular force, even though it has this name. It happens between the hydrogen atom of one molecule, hence the name hydrogen bonding, and the unshared electrons of a different molecule. Now, the other molecule, or both molecules, have to have the hydrogen bonded to nitrogen, oxygen, or fluorine. The reason is because nitrogen, oxygen, and fluorine are so electronegative that when these three atoms are bonded to a hydrogen, they really hog the electrons. And so you can think of the electron cloud, this bond right here, as being heavily favored towards those atoms, and the hydrogen does not get access to them very often. That leads the hydrogen to being fairly positive because it really doesn't have those electrons very often. And of course, an unshared pair of electrons is going to be highly negative. Now, to emphasize this, notice I actually put an entire negative in my drawing and an entire positive. It's not quite that strong. It's not quite a negative one ion and a positive one ion, but it's pretty strong, so I'm emphasizing it here. And notice it's between this unshared pair of this water molecule and the hydrogen of a neighboring water molecule. And this is acceptable and a good example because the hydrogen is bonded here to an oxygen. If this hydrogen is not bonded to an oxygen, for example, if it was hydrogen bonded to a carbon with whatever stuff else is happening, this wouldn't count and it would not be hydrogen bonding. It's got to be a hydrogen bonded to nitrogen, oxygen, or fluorine. And so if you look at this example here, list the intermolecular forces and explain why. Well, LDF, or London dispersion, because it's a molecule, but it's not polar, so no dipole-dipole. And funny enough, the molecule hydrogen does not have hydrogen bonding. Nitrogen has LDF because it's a molecule. It would have more LDF than H2 because it has more electrons. And that's about it. Carbon monoxide has LDF because it's a molecule. It's polar, so it has dipole-dipole. And water is a great example of a molecule that has LDF. It's polar, so it has dipole-dipole. And it has hydrogen bonding because the hydrogen is bonded to an oxygen. And because it's my example in the notes right here. Now, earlier in a prior lesson, I mentioned how we usually assume gases are ideal, but it turns out if we really want to get down to what's actually happening, we have to account for what real gases do, meaning the actual gases that exist in our world. And what happens is we have to account for some problems that occur that we normally don't bother with. First, actual gases occupy space. If you have a container and you have a few gas particles, they don't take up very much space. But they do take up some amount of space. So for example, we usually assume, let's say this was a 1 liter container, we assume the gases have 1 liter to move around in. But that's not actually true. It turns out they actually have a little bit less than 1 liter because of the actual particles taking up a tiny bit of space. So in reality, depending on the problem, it's not 1 liter, it's 0.9 something, something, something liters. And normally we don't have to worry about it. Second thing we have to account for is that the gas particles actually have attractive forces between them due to intermolecular forces. What we assume is that as a gas particle is moving like this, and another gas particle is moving like that, we assume that these two particles don't really have any sort of attraction or repulsion or anything. We just pretend they don't even really see each other in here. And so we don't account for the fact that they're likely going to have a slight attraction, which will cause their paths of motion to not be perfectly straight line, but bent paths. What will happen is this top one, because of a slight attraction, won't go straight. It'll end up curving off a little bit. And this bottom one will end up curving off a little bit up. And that ends up causing pressures that are less than what we would normally predict. Now, two conditions make these two problems worse. So there's two problems. There's the volume problem and the pressure problem. And if you have low temperatures, that causes a bigger problem with the pressure because the intermolecular forces have time to cause a dramatic effect. And likewise, if you have high pressures, that affects the volume a lot because the particles are close. And that means they're actually taking up more space than zero space in the container. So if we want to do it right, we have to fix the ideal gas law. And that's done with what's called the real gas law or the van der Waals equation. So notice this equation is PV equals nRT. It's still the same equation, but there's an adjustment for the pressure and an adjustment for the volume. And if you were asked to do a real gas law problem, you would have to be told what is the A constant, which is here, and what is the B constant for the particular gas you're working with. I don't bother doing that here. It's beyond the level of this class. It's just something for you to be aware of. Moving into the last thing of this lesson. It's called the kinetic molecular theory, and the key word here is kinetic means motion. It's referring to the fact that when you think of a gas, just remember it's in constant motion. The particles are zipping all over the place. They're bouncing into each other. They're bouncing into the walls of the container, and that often helps explain what's going on. So continuous random motion. If you take the equation for kinetic energy, which is 1/2 mv squared, m being mass, v being velocity, if we assume that two gases are at the same temperature, we can say that their kinetic energies are the same. So if you take kinetic energy of one gas is equal to kinetic energy of another gas at the same temperature, that's an important characteristic. You can write out their two equations. So it would be 1/2 mv squared of gas 1 equals 1/2 mv squared of gas 2. I can do a better job and actually label this as M1 and V1 and M2 and V2. Notice the 1/2s cancel each other, and you end up with M1 V1 squared equals M2 V2 squared. And this is known as Graham's law. It's often called Graham's law of effusion, referring to a gas under pressure exiting through a small hole in the container. And you might see it in either version, but the one that people usually use is the one without the 1/2. Now, speaking of temperature, one thing to be aware of is if you ever see the term kinetic energy or average kinetic energy, it's the same thing as the temperature because the kinetic energy causes temperature. And so often, rather than a problem saying temperature, they will say kinetic energy and they expect you to know that. Okay, take a look at this effusion experiment. So what this means is we have a gas in a container. You can imagine any container. So we'll just say, let's just say I have a tube. And this tube has a membrane. And the membrane has little holes in it that the gas can exit. And so it turns out, it says the gas is in here, and it's going to be bouncing around in here all over the place. And every now and then a gas particle just happens to hit one of these little holes and makes its way, and then it goes out of the container. It says a particular gas takes 45 seconds to completely pass through the membrane and exit the tube. Another gas takes 28 seconds. This gas is argon. Find the molar mass of the unknown gas, which was the first gas. Okay. Well, first, when you look at our equation, M1V1 squared equals M2V2 squared, I recommend decide who you want to be gas 1 and who you want to be gas 2. I decided to make my unknown gas 1 and argon gas 2 just because that's the order they were given in the problem, but it doesn't really matter. Then you'll realize we weren't given a normal velocity, but we were given time. And so you can think of it being, as I mentioned here, one event in a certain amount of time or passing through one membrane in a certain amount of time. It doesn't have to be a distance divided by time like a typical velocity or speed. So since it talks about it going through one membrane in a certain amount of time, I said the gas, the unknown gas, went through the one membrane in 45 seconds. And the argon went through the same membrane in 28 seconds. So that's my velocity, even though it's not your traditional distance over time. Don't forget the squares. People often forget that. And then mass in this case will be molar mass. So plug in the molar mass of argon. We're solving for M1. And you get a mass of 103. But according to my numbers here, my time only has 2 sig figs here and here. So the easiest way to fix this and turn that into 2 sig figs is to put it in scientific notation. You get 1.0 times 10 to the 2 grams per mole. All right, another example. Pinhole is made in a container of 2 gases. The following data is obtained. The starting pressure of both gases is 100 millimeters of mercury. And it's noticed that after a certain amount of time, the pressure of gas A has gone down 11 millimeters of mercury and gas B has gone down 22. Well, the fact that gas B, its pressure is going down faster Remember, the gas is bouncing around in here, like so, all over the place. And every now and then it just randomly hits a hole and takes off. The fact that gas B is finding these little holes more often means it must be moving faster. So the faster gas is gas B. And then according to Graham's law, if these two values are going to be equal to each other, the only way that this can happen is if gas B is moving faster. So let's call the one on the right gas B and the one on the left gas A. If gas B has a higher velocity than gas A, that means it must also have a lower mass so that these two values can be equal. This versus my arrows here. And so gas B is also smaller. Now you know this situation actually very well. Let's say you're walking around. Let's say it's passing period. And you're walking along a path, doing your thing. And somebody, let's say somebody's significantly larger than you, is coming along your direction. And let's say you decide to hold your ground. You're not moving. You're not going around them. You are tired of getting out of their way. And you want to hold your own. You know from experience, the only way you can at least tie this person is if you have a higher velocity. Because you have a lower mass, you must make up for that by using a higher velocity. So that at least you can equal them in tie and not get knocked backwards. And you go fast enough, I suppose you would win. I don't recommend you actually crash into people in passing period, especially right now, since you're supposed to avoid everybody and not spread the virus. But it's a good example to help you remember this phenomenon. All right, some review down here. 0 Kelvin means no energy, no movement. What's not ideal about the gas, the ideal gas law? Pressure and volume. Given helium and water, basically when it says who has a bigger A value and a bigger B value, the constants, it's saying who is less ideal. Well, helium is a darn close to a perfectly ideal gas because it's so small, it doesn't take up much space, and it doesn't have very many intermolecular forces. So it is more ideal. Water is less ideal because it's bigger and it has all three intermolecular forces. So water would have the higher A value, and it would also have the higher B value. And unfortunately, homework is very real, and it's right here.